Okay, your next assignment's due on Wednesday. We're also having our exam on Wednesday, and then the project is due on the 19th. I've got office hours this afternoon. If anybody wants to stop by and shoot the breeze about the project, I'd love to look over your spreadsheet or help you discuss assumptions. Just anything I can do to help you with the project, please let me know. So last class was talking about the relationship between price and demand and how that can affect whether or not a project is profitable. And it's not related to any sections from our textbook. But today, break-even analysis is related to chapter 13 in the book. And this analysis is telling us when to switch from one alternative to another. And we'll talk about the details of that, but I just wanted to point out that this is something that you can and should review in the textbook after our class today. Just as one additional reminder about the exam, bring your laptop because you'll have at least one problem where you need to use Excel to do a problem. And when you do use Excel, you're starting from a blank workbook. You can't use a previous example or template file or homework. You just need to start from scratch. And then once again, you're allowed to bring a page of notes. I'll provide the factor tables. I'll provide the equation of time value of money formulas. But then anything else that you might need ought to be included in that page of notes that you prepare. It can be the front and back of a letter-sized piece of paper. Yeah?
Will we need to include any material from the previous exam on it?
No. The exam is just covering the content since exam 1. But having said that, our course is naturally cumulative. And so, for example, find P given A, that is something that I asked about on the first exam, but those kinds of calculations are built in to a lot of the analyses that we've done since then. So it's kind of naturally cumulative, but my intention is to focus on the material we've covered since the first midterm exam. Other questions? All right. So this is a factory making Twinkies, and I show it just to renew our discussion comparing fixed costs to variable costs. And these sorts of ideas apply across all the different engineering fields. It could be the production of food, it could be the production of circuit boards, or it could be in construction projects. It could be service related, or it could be hard goods that are being generated. The idea of fixed cost versus variable costs. But think about when they're producing Twinkies that there's certain things there that they have as an expense that is unaffected by how many Twinkies they're making. So like the machine itself, they have to buy the machine and have it there, and maybe it's something that they're paying for over time, but the person who sold them the machine is getting paid whether or not they actually operate the machine. And then the same thing is true for their rent, and maybe heating the building is a fixed cost, but there are certain things that are variable, like the sugar and the cooking oil and the flour and the plastic, so that if they're making 10,000 Twinkies per day versus 20,000 Twinkies per day, those variable costs would go up with the higher level of production. So fixed costs are those that don't directly change as level of production. So if the number of items sold does not impact how much you have to pay, then that would include maybe like even the salary of employees who aren't working on an hourly basis, then that's considered a fixed cost. So here's a list of some of the fixed costs that you might expect to see. Whereas variable costs are directly influenced by how much you're making or how much you're doing. So it could be the material costs that are going into the production. It could be shipping expenses or the labor costs of the people who make the things. And the more you sell, the higher your warranty costs are going to be, because a greater fraction of the things are going to be maybe need replacement or service or something. So variable versus fixed costs. The reason why we're re-examining this definition is that sometimes we have to choose between equipment that has a big fixed cost but leads to lower variable costs, and vice versa. So we're going to be talking about how you know when to switch from one equipment to the other. The equipment that maybe has a higher initial purchase price but a lower price of operation as your level of production goes up. So here is a figure that just illustrates costs. And the equation is that your total costs are fixed costs plus variable costs. And we did this last time. Remember, we had a graph that represented our costs, and we were intercepting it with our revenue curve and finding those two break-even points. But here, the fixed costs on the horizontal axis, by the way, is Q, the volume of production. On the vertical axis is our cost per unit time. So here you can see the time units is per year. So the fixed costs are the same regardless of your level of production. The variable costs go up. And this is just showing what if you had a linear relationship between production and variable cost. So, you know, like if you are buying flour and sugar and plastic to make those Twinkies, then this linear model just assumes that you get the same price, and that if you double your level of production, then you'd have double the cost. And sometimes that's true. Sometimes there is a linear relationship between production and costs. But in some cases, there's a non-linear relationship where the fixed costs remain fixed, but then look at the shape of that variable cost curve, and then correspondingly, the total cost curve has that same shape. It's just translated above the variable cost curve. Think about what that's suggesting, the fact that it's flattening out. So as it's flattening out, that says that the cost is still going up, the variable cost is still increasing, but it's increasing at a slower rate when you have a higher level of production. So there are certain things in this world that you get a bulk discount for. You know, like if you go on Amazon and buy 100 grams of creatine, then your cost per ounce or your cost per gram is going to be much higher than if you buy a kilogram at a time. And then the same thing is true at an industrial scale. If you buy a pound of flour from Dollar General, you're going to pay a really high cost per pound. But if you buy 5 pounds of flour from Walmart, the cost per pound is lower. If you buy 50 pounds of flour from a restaurant supply company, then your cost per pound's lower again. If you buy a rail car full of flour, then your cost per pound keeps getting lower and lower. And so these nonlinear cost relationships exist when we're getting some sort of a volume discount. So that's usually what would account for a flattening curve, where it's becoming less expensive per unit increase of volume. But there are sometimes occasions where it becomes increasingly expensive, where instead of having a shape like this, so this is the shape that's showing right now, this is cheaper the more you buy. There are occasionally situations where it becomes more expensive, where it starts off linear but then it goes up. Anybody have an idea of why it would get more expensive the more you bought? Go ahead.
The supply of the material we need is scarce.
That's right. It could be that you're buying everything that's available. So this is sometimes the case in the materials that are used for EV batteries, that there can be so much demand that it drives up the price, and then therefore the more you're producing, the higher the cost is. So it really varies from material to material and the quantities that we're talking about. All right. So in class last time, you should be able to reproduce this sketch, by the way. If you ever, like, let's say next Wednesday, hypothetically, had a situation where I asked you to graphically represent the break-even points and the relationship between revenue and cost and everything, the figure that you should draw would be like this. Here's the total cost. Here's the revenue You know, here's our D hat point. Remember D hat we talked about? Here's D prime 1. Here's D prime 2. This is just zooming in on here. So let's zoom in. This is the cost curve and the revenue curve. And when you are to the right of this intersection point, that's when it's profitable. So we like being between D prime 1 and D prime 2. So any place the revenue is higher than the costs, then that means we're going to have profit if revenue is higher than costs. So if we zoom in on this, that first break-even point, remember that we define revenue as the sales price per item multiplied by the number of items that are being sold. So what's going on here is that's the inflection point that defines not covering your costs on the left, and on the right you are covering your costs, where your revenues are exceeding the expenses. And so, like, why is it that if we're to the left side, why haven't we covered our costs yet? Well, it's partly because of this initial purchase price, the fixed costs. So where it intercepts the vertical axis, that represents our fixed costs. So the total costs, remember, are fixed and variable. So what could we do to achieve profitability sooner? Like right now, our profitability is achieved when we are selling 60 units. How could we sell fewer units and still be profitable without changing the revenue curve? Let's say we leave the revenue curve the same. Well, there's two things we could do to be profitable at a lower volume. We could either lower our fixed costs, and then that would bring the whole line down, or we could lower our variable costs, and then that would change the slope of the line. That would flatten it out. Either one of those things is going to bring the point of intersection further to the left. So you've got two moves. Your first move is lower your fixed costs. Your second move is lower your variable costs. And as long as you lower your costs, you'll achieve profitability sooner at a lower volume of production. So is everybody following me so far? Any questions yet? That's what this is showing. This is showing what if we have the same fixed cost, but we lower the variable costs. So the point of intersection with the vertical axis hasn't changed, but now the slope of that line isn't as steep as it was before. A steep slope represents high variable costs. So this is just showing that we used to have some break-even point before, but we found a way to lower our variable costs. So how could we do that? We could switch to a cheaper grade of sugar. You know, like if we're talking about those Twinkies, we could switch from cane sugar to using sugar beets. Cane sugar is more expensive than sugar derived from beets. So if we switch to beet sugar, then that could be a way to reduce our variable cost, or make the plastic thinner. Or we could pay our workers less and be really sinister about this. Well, whatever the case may be, if you lower your variable costs, then you're going to be breaking even sooner and you're going to have more profit. So this is just the equation I think we also looked at yesterday, where it was the intercept with the vertical axis divided by the revenue per unit and the variable cost per unit. That'll tell you the break-even point, the first break-even point. So you lower your cost curve, it shifts the break-even point to the left. So that's another thing you should commit to memory for any upcoming assessments is, you know, like what is the cause and effect between lowering your variable costs? What effect would that have on your break-even volume? Lowering your variable costs reduces the break-even volume. Okay, so the break-even has two different interpretations. The first interpretation is the break-even between profit and loss. And that's what we're talking about here with this figure. The next figure is talking about a different kind of break-even. It's talking about the break-even between two different options. You know, should you choose option A, should you choose option B? And so what we're looking at here is two different cost curves. And so this slide was a revenue curve, one revenue curve, and then like a single cost curve that was then subsequently lowered. So this figure has a revenue curve. This figure doesn't. This is just two different cost curves in this figure. But same axis. On the horizontal axis, we're talking about volume of production. Vertical axis is cost. But here, alternative 1 has a cheaper initial purchase price, but then when you actually use it, it's more expensive per unit of production. Whereas alternative 2 has a more expensive initial purchase price, but then you can use it with a lower cost per unit production. So let's just go back to the idea of phone cases. If I was going to try and start a business to produce phone cases and I wanted to use a 3D printer to produce them, 3D printers are pretty cheap these days. They're not really expensive. You could buy a 3D printer at a pretty low cost, but then the actual operating expense for each phone case that you manufactured would be high because you've got to buy the plastic, the electricity. It kind of takes a while to do and so on. Whereas if you got some sort of a plastic injection molding system, it has a more substantial upfront initial purchase price, so the fixed cost is higher, but then it's cheaper to use once you've got it. So that would maybe be a real-world illustration of option 1 versus option 2. So there's a certain level of production where one option becomes preferred versus another. So if you're just going to do a little bit of volume, then maybe having a 3D printer is okay. So if you want to minimize your costs, like where are the two costs, where are the costs the lowest? And so to the left of this intersection point, alternative 1 is cheaper. It has the lower cost. But then when you get to this point of intersection and you go to the right of it, now option 2 is the lower one. And it's a little confusing because they changed the colors. But the point is, to the left of the break-even point, option 1 was cheaper. To the right of the break-even point, option 2 is cheaper. So sometimes the analysis is, how many units do we have to sell to where it becomes justifiable to buy the more expensive equipment? If you're going to be making a lot of them, then maybe you ought to get the more substantial equipment. So does everybody understand the two different kinds of break-even? There's the break-even between profit and loss, and then there's this kind of break-even, which is the break-even between alternatives. So this class is all about decision making, how to choose one thing versus another, and how to make decisions in a systematic way. So this analysis is a way for us to know whether we should get the item with the lower fixed cost but the higher variable cost per unit, or whether we should spend more now to save money in the future by having lower variable cost per unit. So the break-even point is where the two alternatives are the same. Okay, so let me give you our in-class exercise for today. And by the way, there's a template file on Blackboard, and if you downloaded it before today, you should delete that file because it has the answer in it already. I forgot to upload just the blank template. So I re-uploaded today the template file that just is, it has all the formatting and cells and everything, but not the final answer. Okay, so I think that the template file maybe speaks for itself, I'm going to give you a few minutes to try and figure it out on your own without any narration or guidance from me. And then, of course, I will break in maybe 10 minutes or something, and we can start to go through it together. But what we've got, just to discuss the setup, is we have two different alternatives. Some equipment that's computer controlled, that's expensive, that has a high upfront first cost. And then we've got a manual controlled option that has a lower first cost, but higher labor costs and lower productivity. So look that the two items have different output. So the computer controlled equipment can do 3 things per hour. Whatever it's making, it makes 3 of them an hour. And so like if you're going to make 1,000 things, option 1 will do it in fewer hours. Option 2, since it runs at 2.4 units per hour, it's going to take more hours to make the thing. And so when you compute the labor costs, you have to know the cost dollars per hour of labor, but also the number of hours of labor that are going to be required. So I just wanted to point that fact out, and that also they have different useful lives. And so when you calculate the capital recovery, N is going to be different for option 1 versus option 2. All right, I'm just going to type in what we know about these two different options. And since we're calculating capital recovery, we need to pay attention to sign. So for example, for this first cost, I'm going to put negative 2 million. Okay, just starting with the assumption of 1,000 units, and the problem statement said that we've got a MAR of 9%. If this option 1 equipment can do 3 units per hour, then that means the number of hours per year it's going to be running and operational is 1,000 units per year divided by 3 units per hour. So that tells me it's going to take 333.3 hours of operation to make 1,000 units. Whereas option 2, to make 1,000 units when you're only going at 2.4 units per hour, it's going to take more time, 416.7 hours of operation. So that's really the first thing, is just knowing how to use this equipment productivity factor that's provided. Please feel free to interject if you have any questions. All right, capital recovery. Remember that capital recovery is where we are annualizing the difference between the initial purchase price and the salvage value. So we know that there is some cost that we have to pay now to buy the equipment. So we've got an outflow at time 0, and then a certain number of years, and then we get an inflow here in the future when we sell the equipment. And we want to know what is the annual equivalent of that. What function do we use in Excel to find an annual equivalent? PMT, right, the payment function. So PMT is where we want to find A given P and F at the same time. So the fixed cost capital recovery equals PMT. We'll put in our rate here is 9%. I'll anchor that reference. NPER, Number of periods. Okay, so that's the predicted life of option 1. The present value, that's the initial purchase price, and so the negative of the first cost. And then the future value is the salvage, so that's the negative of the salvage. And so what that's going to tell us is how much we have to pay per year to own that equipment. Okay, so instead of paying $2 million up front and then getting back $150,000 in 10 years, that's the same, economically equivalent to paying $301,000 every year. All right, and I think I can drag this formula sideways and have it applied to option 2, because the reference to the I value is anchored, but then everything else will be relative. If I just drag that formula to the side, then it'll do the same thing for option 2. So option 2 has a lower capital recovery just because it's so much cheaper. What's the rule I've told you about comparing things that have a different useful life? Has to be the same study period if we're doing present worth analysis or future worth analysis. But if we are doing annual worth analysis, then it's okay to compare things with a different useful life, as long as the assumption is that it's repeatable. So here, what we're doing, we're comparing option 1, which lasts for 10 years, and option 2, which lasts for 7. Since we are annualizing that, it's okay for us to compare them, even though they have different useful lives. Let's just assume that we could go out and buy another version of option 2 sometime in the future once it wears out. I just wanted to acknowledge that. Okay, so we got the fixed cost. I don't think recovery is spelled right. Recovery, is it A-R-Y? Recovery?
No,
Is that right?
Yeah.
All right. It just didn't look right to me. I don't know. All right. You know, when you misspell a word in Microsoft Excel, it underlines it in red, but it does, no, in Word, it underlines it in red. But in Excel, it doesn't automatically spell check. So I'm always paranoid when I'm using Excel. I've got misspelled words in there. All right. Now, variable cost. So this is just dollars per hour of labor and how many hours per year it's running. So dollars per hour multiplied by hours per year tells us dollars per year in the variable costs. Okay, so then the total cost would be the two added together. Oh, it still remembers the conditional formatting. I wish I had deleted that as well. It's automatically going to highlight the one that's higher of the two values. Just as a reminder how conditional formatting works, select these two and you do home, conditional formatting, clear rules. Let's clear from the entire sheet. All right, so home, conditional formatting, new rule. We want it to choose the top one. So it's going to be the value that's the biggest or the least negative. And then what will it do? We want it to be bold and maybe fill it in with a yellow highlighting. Okay. So now this is being selected because it's least negative. It's the top value. And then let's calculate the difference between the two. So just one minus the other. And that's useful in case we have to do a goal seek, because our goal would be to bring the cost difference to 0, and we can use that to find the break-even point. So that's why that cost difference cell is there, is for us to use as a goal seek parameter later on. Okay. So here on the handout, it's asking for an expected output of 1,000 units per year. What's the total cost for each alternative? So $362,000 in cost for option A, option 1 it is, or $340,000 for option 2. So if we're going to run at 1,000 units per year, which one should we select?
Option 2.
Option 2. So let's just, let's say if the expected output is, oh, this is referring to the break-even point. So let me just write an answer to kind of like a comment related to Part B here. Part B, note, at 1,000 units per year, option 2 is less expensive. All right? It has the lower cost. Now that we've got this set, we could just put in 3,000. Oh, let me actually put the value in here. The cost is $339,547.67 at 1,000 units per year for option 2. All right, so now I've got that preserved, because when I change the output, all the other numbers are going to update as well. If we switch to 3,000 units per year, look how the highlighting has now changed. It was option 2 that was highlighted, but then when I put in the 3,000 units per year, now option 1 is highlighted because it's the cheaper option. If we go big and we're producing a lot of units, then option 2, which has the higher initial purchase price, that initial purchase price is justified because we're taking advantage of a higher level of production. We have lower cost per unit, so it becomes cheaper overall. So at 3,000 units per year, I'm just putting a comment here, option 1 is less expensive. $481,767.17. This is because the higher initial purchase price is offset by the lower variable cost. So its variable cost is lower because the labor cost is less and you have more productivity. So you're using fewer hours. So it's fewer hours and every hour is cheaper. You're only using 1,000 hours at 180 per hour instead of 1,250 hours at 195. I've been doing a similar thing recently with tires, a similar analysis. I've got it narrowed down to either the Goodyear Assurance Max Life tire, which has an 85,000 mile warranty and costs $147 per tire, or the Goodyear Assurance Reliant tire, which is I think like $120, has no warranty, but they expect it should last about 55,000 miles. And so like I'm trying to figure out like what's the break-even point? How many miles do you have to drive to where the more expensive tire becomes the better option? And I think what I came up with is that as long as I get about 65,000 miles on the more expensive tire, then it becomes economically the better alternative. So that's kind of a similar example to this, is you've got a more upfront cost, but it lasts longer. Is that justified? Like, what's the break-even point? Yeah?
Do you use spreadsheets in Excel to analyze your life pretty regularly?
I put my money, all my assets and expense and stuff into Excel pretty regularly, but like that the tire thing, I had AI do that one.
Okay.
Yeah. But I know what it's doing, so when it inevitably screws up, I know when it screws up.
Okay.
I wouldn't put it into AI if I didn't already know what I was doing in the background. So I could have done it in a spreadsheet, but just to be honest, I do use AI sometimes. Yeah.
I appreciate your honesty.
Yes, yes. That's a good question. All right. So that's C. Now what about D? Using goal-seek, what is the expected output that makes the two options equally expensive? So what that's saying is, what is this point? What is the QBE? Q is volume, like the level of production. What's the BE, the break-even point, where it makes, it's a toss-up. We know it's somewhere between 1,000 and 3,000 because at 1,000 it was option 2. At 3,000 it's option 1. So we could, just try it out. Is it 1,001? No. Is it 1,002? No. 1,003? Like, what we're looking for is we want this cost difference between options to be 0. So, data, what if analysis, goal seek, and our objective here in the goal seek is for this cell, which is the difference between the two, to be 0, and it should change the output. So it's going to just keep playing around with Q, the volume of production, and it's looking for when does the cost difference between the two close to 0. 2,045.62 units. We can't make a fraction of a unit, so we just go to the closest one, which is 2046. So they're approximately equal if you're making 2046. And so down here, let's fill this in. If the expected output is less than 2046, then you should purchase option 2. So if you're doing like a low level of production, then you want to minimize your initial purchase price. However, if the expected output is 2046 or more, then you should select, option 1, because that would be the option with the lowest total cost. All right. Any last questions before you start your weekend early? Yes?
Yeah, I assume this is meant to be used with the homework. I solved it in a completely different way. I already submitted it. As long as I get the right answer, is that okay? Because some of the answers are given and I got those answers.
Yes.
Okay.
Yeah. You don't have to use the template. Just when I give you a template, that's not like a mandatory thing to use. Yeah. Other questions? All right, that's it. I'll see you on Monday. Have a good one.